Okay. Yeah, can you see my window?
Yeah.
Yeah. So good morning. Thank you very much for organizing the conference and for inviting me. I have to say that I'm a bit disappointed to be here at home and not in Tübingen. But I'm living in a variant virus area. And this means that I cannot, I could come to Germany, but then I have to isolate for 10 days. So spoiling the purpose. So yes, it was very interesting. Once I've seen Peter's talk, I realized that maybe I should give him a completely different talk, because I've recently done some work on models of quotient inductive types using containers. That was also subject of my talk recently at the types meeting. When I heard about this Gödel meeting, I thought, oh, maybe I get a bit inspired by this general idea of incompleteness. So, And I should say what I'm going to talk today is some recent ideas I had, and they may not be may not make sense or work out or whatever, but I thought it fits very well with this workshop. There are actually ideas I have been thinking about since a while, and so I thought maybe it's a good way to present them. Gödel's theorem tells us somehow that we cannot really hope for completeness in his sense. But I think the quest for completeness is quite interesting. So we find that something is, we present a logical system, foundational system, which somehow is incomplete, and then we want to add something. So it's a path of making your theory more and more complete, which I think is interesting. And I will try to reconstruct some recent developments of type theory from this perspective. My first is just a little note, which I'm sure many people are aware of, that when we think of incomplete systems, we usually, obviously any subsystem of primitive recursive arithmetic is incomplete. But when I'm in an intuitionistic system, actually, it turns out that already propositional logic is incomplete. So actually, I have to say second order propositional logic. So in the sense that I can quantify over propositions, now I don't need impredicativity. So I can have a second order propositional predicative second order logic, which is present in modern type theory, where we have a type of propositions like in a Hort, and all propositions don't form a proposition, but they form a bigger type. Well, that's okay. So now I can express as excluded middle as this quantified proposition for all prop I have P or not P. Now we know that EM is not provable. So how do we know this? So we know this from Kripke models or pre-sheaf models of type theory. But neither is not EM because we do know that type theory is compatible with classical logic. Yeah? So we can add classical logic, and it's fine. Classical logic. By the way, what do we mean by classical logic? If we don't want to take this Boolean interpretation, we can have a negative translation, which is completely constructive, and we can show this is a model of everything we have, which satisfies this little middle. So we cannot prove EM, nor can we prove not EM, and clearly that's a witness of incompleteness. What can we do? We can overcome this if we want to. We could add EM or another classical principle like reductio ad absurdum, not P implies P. But that's maybe not in the spirit of type theory of constructivism. Another alternative is to add an anti-classical principle, like church thesis, which is maybe more natural. So what does it say? It says that for every function on the natural number, there exists a code which computes this function. Well, no, there was actually a recent discussion to formalize this n computes f is quite a nice little job, maybe a nice project for a student. And by the way, this is not, some people always think this is inconsistent with extensionality. That's not the case, because we really need to use exist here, which forms a proposition, and not sigma, which actually lets us observe the witness. So this formulation is well behaved in type theory. And since we know that the holding problem is undecidable, we can show not EM. It's not the case that exclude middle always holds. But to be honest, in type theory, we are not really, I think we're not too concerned about this. Actually, we prefer to leave this question open, to embrace incompleteness in a sense. We don't add either. So we like to stay compatible with classical logic, but we also allow ourselves to add something like church thesis or a local continuity or whatever. However, I want to talk about other kinds of incompleteness, which I think play a more important role in type theory, and which have to do with equality. And here I would like to cite Leibniz, who I don't have the precise quote, but he says objects which are indiscernible should be, which I could not differentiate, they should be equal. Or we could say more positive. If we have two mathematical objects which have all the same properties, then they should be equal. And this is, I think it's particularly interesting in type theory as opposed to set theory. Because in type theory, we can only define certain properties. We could say structural properties. And hence, it allows, or actually forces us, in the sense of Leibniz, to identify more objects. So, okay, how can we express this? So Leibniz principle is often expressed using second order predicative logic as follows, and that's also often used in the definition of equality as Leibniz equality. We say for any predicate on, if you have two objects of a type A, then for any predicate on A, if the two applications of the predicates are equivalent, then A should be equal to B. Yeah, we can replace equivalence with applications, but just leave it like this. But this is not a good reflection of this idea, because it's trivially true, right? As we know, because it's a tautology. If you have equality, we can just instantiate P is X being equal to A, and then the conclusion gives us that A equals A is equivalent to A equals B, and then we just need the left to right direction and reflexivity to conclude A equals P. So the challenge is somehow, how can we express this idea that we want the two objects which have the same observations are equal? Now, I don't know whether this is the final answer, but here's one possible suggestion. And I also want to talk not internal to type theory, but I want to talk about type theory. So here's my suggestion. So one thing is I replace prop by bool, so I'm only talking about observable properties, decidable properties. And here I say if for all definable decidable property these are equal, then the object should be equal. So two objects which have the same decidable properties should agree. Yeah, I'm not 100% sure that this is the best way to express this idea, this Leibniz idea, but let's go with it. This is not a tautological property, actually, unless you assume it to the middle, because then bool and prop is the same. And I think we can use it to observe already that what is known as intensional type theory, or ITT, is in a sense incomplete. And it's incomplete in this sense of this Leibniz word. Namely, that the principle fun-ext, functional extensionality, is not provable. And we can express it as follows, given two functions f and g from A to B, if for all, if these two functions agree pointwise, then they should be equal. So now, this is not provable, and it's actually quite easy to see. It's not even provable in intensional type theory. And this follows from the fact that the only way to prove an equality in the empty context is to use reflexivity, because it's a constructor of equality. But we can only use reflexivity when both objects are actually identical or definitionally equal. That means just use two functions which are provable equal, I mean pointwise equal, or for example x plus 0 and 0 plus x. So then you can prove the premise, but you cannot prove the conclusion. So it's the argument intensional type theory doesn't prove fun-ext. On the other hand, and that's, I find out just a paradox of intensional type theory, and that's this incompleteness I want to refer to. It doesn't provide any observations to distinguish externally equal functions. So we cannot, we cannot prove them equal, but we cannot observe anything which differentiate, which makes them distinguishable. So in this sense, we can prove, we have two functions which we can prove are equal, are extensively equal, but then for any predicate, any observation on them, they will agree. And so we can prove this by showing that there are models of intensional type theory which satisfy all principles, but also prove fun-ext. And an example is the Setoid model, which we have also recently investigated in more detail, where types are modeled as equivalence relations. And in particular, the equivalence relation, the equivalence relation here corresponds to the equality type. And in particular, the equivalence relation of the function type is equivalent actually to functional extensionality. And hence we can see that in this model we cannot distinguish them. So hence we cannot distinguish them in intensional type theory itself. Okay, so the Setoid model also provides constructive justification for another principle, which is also interesting. It's so here I used prop. So what we usually do, we add prop as a type of strictly irrelevant types. And we can show this principle, we can justify this principle that two propositions are logically, if two propositions are logically equivalent, then they're equal. And I think that's a very natural idea, because we want propositions. The only thing which matters about the proposition, also from the point of view of type theory, is whether it's inhabited. And we don't want to allow any more observations or propositions. So we have this principle prop-ext, which can justify this principle, which says that if two propositions are logically equivalent, then they're equal. And in this context, a prop is also what's something called H-prop. That is, it's a proposition, it's a type which has at most one inhabitant. So I could, using a notation which looks, which is a sigma type written using curly brackets, actually, we can define prop as a type together with a proof that any two inhabitants are equal. So again, we cannot prove prop-ext in intentional type theory, even with a type of propositions, even assuming that we have a type of propositions, but we cannot prove that any two propositions which are logically equivalent are equal. But we can justify this principle. We cannot observe. So if we have two propositions, in the sense, we cannot observe any difference between two equivalent propositions. So that's another Leibniz incompleteness. So we can add these principles, and in this work on Satoid type theory, we show that we can do this. Oh yeah, I should remark that there is. We could also say, I mean, there's always the choice. If you have this incompleteness, you have this principle. Let's just think about FunExt. So we can either add it or make it relevant. So we can destroy the precondition by actually add observations on functions which break extensionality. And that is what I would call an intentional version of church thesis, which is often taken as the only one. Namely that for every function, we have a sigma type. So we replace this exist I've used previously by sigma. So it means for every function, we can actually see its code. And that contradicts FunExt, because we need to assign the same code to extensionally equal functions, but that's not decidable. We don't know whether two functions are extensionally equal. Church thesis, on the other hand, tells us that we can only do decidable things. So an intentional version of change thesis breaks this, but I think it's more interesting from a point of view of type theory, more natural, to really add FunExt. So not to allow, okay, why is it natural? Because a function in the sense of type theory, to me, is a co-inductive type. So we are not understanding function by the way they are defined, but what we can do with it. And what we can do with the function is applying it to an argument. So two functions which behaves the same under application, and that's exactly what FunExt expresses, they should be identified. And using this Satoid type theory, using this model, the Satoid model, which can be formulated in type theory itself, we can formulate a type theory which supports FunExt and prop-ext. And we have recently, also with Ambush and some other people, investigated this type theory, SAT-TT. Okay, but let's go further, and that's an important step. We can go further and observe that in ITT, but also actually in SAT-TT, we cannot distinguish isomorphic structures in particular, let's talk about sets. So now, okay, there's a confusion when I talk about sets. I don't mean the sets of set theory, but I talk about types whose equality is the proposition, and that seems to be quite natural. So I formulate this like this, again using this notation. A set is a type together with a proof that's a proposition, and we can spell this out. It means that any two proofs that two objects are equal are themselves equal. So it's a principle. And so normally you would expect equality to be propositional. And by set isomorphism, I mean the usual notion. I mean, you have functions in both directions, which gives the identity, and then they're isomorphic. So, for example, we can define the type of natural numbers using either the usual piano definition with zero and successor, or alternatively, we can use binary natural numbers. So here's a concrete representation. There's a bit of a trouble with zero, actually. So I first define the non-zero binary natural numbers, and then I add zero. So that's one way to do it, to avoid any problems with leading zeros. And actually, it's clear to see that these two types are isomorphic. And it turns out that no construction in type theory can distinguish these two types. And that always confuses people a bit, because they look very different. They're defined in very different way. However, if I just give you a type, then you would have to define an observation on this type which distinguishes them. And that turns out is not possible. They're completely replaceable one by the other. Yes. We can show that it's unprovable, and let's go to the theory with has some extensionality like ZTT, and we actually have recently investigated a universe of types in ZTT, which is actually an inductively defined universe, and I think we haven't done this, but it should be possible to use this universe to show that we can distinguish isomorphic types because they look different. So that means that this is not this principle that isomorphic types should be equal is not provable in ZTT, for example. But we know that they are Leibniz equal, and that's actually a bit older in this case. So this was Hoffmann-Streicher's groupoid model, and they observed that the groupoid model basically shows that we can consistently model of equality of types using isomorphism. And that using the same argument as I've given before, I think shows that isomorphic types are Leibniz equal. And actually, Wodzki went further and stated a more general principle which applies to types and not just to sets, and which implies in particular that isomorphic sets are equal. It also, by the way, a special case of this univalence principle is also prop-X. So if you apply it only to proposition, you get a propositional extensionality as a special case of univalence. What have I done here? yes, but as I think people who have studied Hot knows that identifying isomorphic sets already forces us to allow equalities that themselves are not propositional. So, for example, that it and Boolean negations are isomorphisms showing that bool equals bool, but they cannot be identified. And that's interesting because it shows that we need a more general notion of equality of types, which is called equivalence. I don't want to go into detail here, but we see that not every type is a set in the sense above, but that there are types which have equality, which is itself not a proposition, but a structure. And this principle. So I'm calling it a principle because I'm not calling it an axiom, because I don't think axioms have anything to do in type theory. We should always have principle which can be reduced. Right? And Wołodzki's univalence principle goes further and works for types which are not sets, and basically replaces the notion of set isomorphism by equivalence, which in a sense is actually isomorphism, but for higher structure. Set isomorphism, but groupoid isomorphism of infinity groupoids. Okay, so I think I mentioned this already, that, okay, yeah, so the Leibniz incompleteness follows from the existence of interpretations of type theory. So originally justifying this univalence principle. And originally this was done by Wołodzki using simplicial sets in a classical meta theory, but later by Thierry and other people, sorry, complete list here, that cubical sets are constructive. And there was a bit of a question because the equality in cubical type theory is not the same as equality in intensional type theory. But I think that's not a problem because we can also model the intensional equality, which is then equivalent to the what's called path equality of intensional type theory. So that shows that in a sense, the lack of univalence is really an incompleteness of intensional type theory, but also of more extensional type theory like ZTT, which can be overcome using Hot, using implementation in terms of cubical type theory. For me, cubical type theory is a way to make Hot more precise and also constructively well behaved. Okay, so one can ask, so is this all in a way? I mean, okay, maybe another question which comes up is Leibniz completeness achievable? And I suspect not. I mean, I'm sure there is a proof similar to Gödel's incompleteness showing that we cannot have Leibniz completeness, but we can ask how Leibniz complete is now Hot, because it seems to be much better than intensional type theory and much better than Satori type theory. Have we reached sort of like a natural point where we should stop, and maybe we should stop. However, there are some examples of equalities you may want, which don't follow from Hot. I think they don't follow it away. I'm not sure how to prove this. Actually, maybe there is a way. Specifically, these are the so-called free theorems, which are quite interesting because univalence we can explain by the idea that we cannot look into a type. We can only do things with types, and we cannot look into them, which justifies to identify the types which, as I said, are observationally equal. But free theorems also exploit the same idea that you cannot look into a type, So hence, if you define what's called a polymorphic function or function indexed by a type, it cannot actually depend on the type. And a simple example is this: if we have a function which has the type of the polymorphic identity, so for all x, etc., could be a type, it doesn't matter. It goes from x to x, then it should be true that this is actually the identity function, because the only function really you can define of this type is the identity function. So that's a theorem for free. And in general, you should be able to prove naturality properties. So anything which looks like a natural transformation in the sense of category theory should be one. And the question here is, can we prove free theorems, for instance, of Leibniz incompleteness? I think it should be possible. I've conjectured recent work. There's some recent work on parametricity and Hot. And another idea is to use directed types theory, because in Hot you can prove that this sort of principle holds for equivalences instead of functions here. So equivalences are always natural, and that follows from univariance. So hence, it should be a consequence of a directed notion of univariance that naturality holds. But that's also interesting, because so far, everything we did was actually compatible with classical logic. So Hot is still compatible with excluded middle, but free theorems are not, because we can really write, we can, using excluded middle, to write functions which are not natural, which depend, so depend on, behave different on different types. So that's interesting that if we add this principle, if we go a bit further, then we also become anti-classical. Okay, so I'm actually at the end of what I wanted to say. So to me, the Gödel incompleteness, I would say, has a different flavor of this Leibniz incompleteness. So we can always, we can overcome this notion of incompleteness, the Gödelian one, by adding reflection principles, by adding universes. Whereas this Leibniz incompleteness, which I tried to capture, is more of a structural nature. Yeah, it's really, there's some. Once we define these objects like types and so on, then we should really have an equality. We either should be able to distinguish the objects, or if they're indistinguishable, then we should identify. It's somehow different notion. And this is, as I said already earlier, this is particularly interesting in type theory, because in type theory we can only state structural properties. So actually, objects which behave the same way, which are structurally the same, need to be identified. Okay, that's all I wanted to say.